Welcome to the Tomorrow's World Today podcast. We sit down with experts, world-changing innovators, creators, and makers to explore how they're taking action to make tomorrow's world a better place for technology, science, innovation, sustainability, the arts, and more. In this episode, George Davison, who is also the host of Tomorrow's World Today on Science, talks with James Walker, President and CEO of Nano Nuclear Energy, about the groundbreaking future of nuclear power. Discover how portable nuclear reactors are set to transform the energy industry, paving the way for cleaner, more reliable, and sustainable power solutions.
Welcome to our show. It's great to have you here, James.
Oh, no, thank you very much for having me on the show, George. Very pleased to be here.
Well, I'm hoping that you're going to share with our audience a little of your background and your position, your role at Nano, and then maybe we could get into the details a little more about what Nano does.
Absolutely. Look, I'm happy to share all of that. A little bit more about my background. I'm a nuclear physicist and nuclear engineer in the past, and I got my start in the submarine program, where I was involved in secondary and primary systems for submarines. And I was seconded to Rolls-Royce for a little bit of time, where I worked in the reactor physics and thermal hydraulics departments in the design of reactor systems. And eventually I was promoted out of that role, and I ended up at the Ministry of Defense, where I was involved in building the manufacturing facilities to mass produce these reactor systems to go into the next class of submarines.
That's pretty exciting, James. I don't mean to interrupt you, but that's really fun. So I
agree. It's a very especially when you get into things like reactor physics, it can be very technical, but it's still very interesting. And I think nuclear physics and nuclear engineering is a very interesting subject. Well, of course I do, because it's my job.
Yes. Yeah. Well, and it's an emerging area, so I'm hoping we can peel the onion back a little bit on that today. So what does nano nuclear energy do now that you're not on submarines or making submarines anymore? Can you walk us into that world?
Yes, absolutely. So a few years ago, I was living in North America, and I was building manufacturing operations. And through that network, I met the founder of the company, and who had a bit more of a background in banking. And his thesis was that nuclear would have resurgent interest in the next coming years, because the power that would be required by the country was quite substantial, and the means to supply that power was actually not there at all. So if you were looking at everything, so solar, geothermal, wind, hydro, upscaling gas or coal, it was very difficult to see a way to actually meet the demands of industry and domestic infrastructure as well. So we knew that nuclear was going to make a big resurgent comeback into the frame. And so we looked at where the company could position itself, where it could be the most successful, because we knew that there were a lot of companies building small modular reactors, which are fairly big systems. But we saw that actually microreactors, they were the least developed part of the industry, and potentially the much larger market, because if you were to build a microreactor, so you're talking very small nuclear device now, and you could cater for military bases, mining projects, remote oil and gas, island communities, remote habitation, other remote industry. It's $1 trillion industry where these diesel generators are catering almost exclusively for all these projects and communities without any competition. And we thought that a microreactor could be inserted into these areas, and if we were successful, it would be an enormous market. And with the right financing structure and the right personnel, we could pull out into the race of producing this product first.
So when you say small, right, or I guess that's why it's called nano nuclear, but give us a sense of scale. When you say, I think most people, at least in North America, they have pictures of those big silos that they see from the road, and that's probably what is in most of their minds. So can you give me a sense of just how small we've gotten here?
Yeah, so and look, the conventional civil nuclear power plant, that's what we're all familiar with, with the big plumes of steam coming out of the funnels. But microreactors are tiny by scale. So we're talking really with an ISO container sized dimension. So when you're going down the highway and you're seeing trucks just shipping the standard containers, that's the scale we're talking about here. We want to get the core and the turbine system into one ISO container. And the reason for that is deliberate. If we can fit everything into an ISO container, then we can move it by road or by rail or by ship anywhere in the world. And then essentially what we wanted to basically get it to somewhere where we can put it down and plug it into a local microgrid. And the construction at the deployment site would be minimal, if anything. And if we do that, then we can begin to compete with diesel generators.
That makes sense, because those are transported around on trucks. So that's a good vision. How close are you to achieving that vision?
So I think we're pretty advanced. We've gone through all the detailed design work. We've done all the computer models, the physics verification of what we're trying to do. Now we're moving into a very different phase where we're going to be building prototypes and rigs, and we're going to be doing data collection so we can go to licensing. So it's shifted into a very different arena now. And I think we're not unique exactly, but one of the very few microreactor companies in the world that are in this stage, where we're taking it out of the academic exercise and the design phase, and we're going into demonstration work. So we're building rigs, we're doing irradiation testing, materials testing. So we're just validating all of our models. And once all of that's done, we'll build a prototype and we'll get that licensed, and then we'll commercialize it and deploy it.
So in the world of, let's say, going to where we are now with diesel generators that are fulfilling a function of generating power for all the different needs that we have, be it a computational farm, for the internet or whatever, those things, they consume a lot of energy. But if I was to ask you, if I put a diesel generator there, I get X, and it's in order to do that, I have to do a few other things. I have to continually put fuel in it. I have to do some things to make it go. But if I go in this other route, which let's say it's the same footprint, it's mobile, what would you say are some of the benefits if it's me and I own this facility where your device is coming in versus a diesel generator system? What's the advantage to me as the owner?
So it's actually a very good question, because this is the marketing we want to use. Is that, let's take a couple of examples. So we spoke to the governments in the Philippines, and they have the most expensive power in the whole of Southeast Asia. And that's principally because they have a lot of island communities. And Indonesia kind of has the same issue. And that means that they all subsist on diesel, and they need to basically bring in diesel on a daily basis. And that is very logistically complicated. It requires a lot of personnel, and it's expensive. Now, if you were to have a microreactor in these sort of situations, that means that those island communities have a consistent baseload power for 10, 15 years, and the whole logistics around that daily importation of diesel goes away. Now, that's true for any remote project. So if it's a mining project, they still need to bring that diesel in, and that can kill a lot of the economics with regard to those projects. And so, and you see that mirrored in things like military bases. Like the US military has a mandate that the military bases should be able to be self-sufficient for at least a 2-week period. And currently, I don't think they can meet that mandate, because they still have to subsist on a lot of these remote locations on diesel, and they can't bring in 2 weeks worth of diesel at any one time. So there's all these different areas where microreactors will have a significant advantage over bringing in diesel. And just reverting back to the Philippines, that's true for Indonesia and Thailand, where they've got between them hundreds of millions of people scattered across hundreds of islands that subsist on diesel. But that also means that there's blackout periods, there's loss of power, there's delays in the delivery. That means that there can't be, the industry suffers there. So it's not just a way of giving people more consistent power, it's a way of actually ensuring that industry can take off in these areas.
Right, I got you. So let's say that I have this rectangular box and I've got my nuclear power in here. How long, if you put one of these in it, let's say that the military facility, how long can I get power? And given that we're drawing on it about at an average level, let's say, how long can you get out of that?
So some of the calculations that we've done on the operability of the reactor at about average level is about 15 years. And if you're running it obviously a bit more intensively, it would still be around about 10 years time frame. So if you were running a community, which is a fairly consistent level of requirement, you could go as high as about 15 years of power output from these reactor systems. Obviously, that saves you 15 years of logistical work around, bringing the fuel.
Right. Yeah, it's not just the cost of the fuel; it's all that logistics, all that chaos, the instability if something happens to that truck getting there or helicopter dropping something in. It sounds very exciting. So I guess you're pretty familiar with this. Maybe it's because of part of your background with submarines, because they've had nuclear powered submarines for a long time now. Did you have a knowledge transfer from that world over to this world now?
Yeah, so certainly the principle upon which all reactors work, fission reactors, is the same. So it's still uranium enriched to a certain level, and that fission process obviously creates the chain reaction that creates the heat, and then that heat can obviously be converted into electricity as needed. The submarine reactors are obviously a little bit different. They can use a much higher grade of material because they're for military purposes. And obviously the reactors that we'll be building with are a much lower level of enrichment. There's certain reasons for that, but principally it also makes them inherently safe reactor systems. These reactors we're putting together cannot blow up. They cannot be turned into weapons. They are an intrinsically safe technology, whereas a submarine reactor, you would want to guard the fuel in that much more closely. And obviously you are, because you're in a submarine, so it's very well guarded, but it's a much higher level of enrichment.
So I imagine that is a very important part of your design, public safety, because these things could be dropped in anywhere. And what I just heard was that you really can't tinker with them to make them dangerous. But go ahead.
Oh, no, I was just going to say, we do, of course, I think the communication with the public around about the safety with nuclear is very important. And just communicating the fact that these systems cannot blow up. Some of the disasters that you've seen, say in America, like 3 Mile Island or something like that, are not possible with these sort of designs. They are an inherently safe system. So you can deploy these things to the middle of nowhere. And we even get asked questions about what happens if this blows up or a terrorist takes it. And the response is that if you were to blow up the reactor, like fire a missile at it or something, the reactor actually becomes cooler because you separate the material, so it becomes less critical. And if a terrorist was to steal it, I mean, I don't know what they would do with it apart from warm their house, because you'd have to take the fuel out, separate it with a big chemical process, enrich it, deconvert it and fabricate it. And you'd need billions of dollars worth of capabilities to do that. And I don't even think the US government could do that itself. So it's a terrorist can steal it all day long. It wouldn't really make a difference.
Gotcha. So in your world, your organization, you probably need up and coming scientists, physicists, engineers, that type. How is that going? Are you getting enough young up and coming people that can really help support the growth of your organization?
Yes, we actually have. It was a major concern of ours, because what happened with nuclear is after Fukushima, there was a decline in interest in nuclear, and that led to essentially what we call the middle of the nuclear employees leaving the industry and then going to other pastures. And so you have now in nuclear, you've got the older generation, which I think are really the backbone still of the nuclear industry, and then you've got the new incoming people coming in now. But because of this resurgent interest, there's a big fight for those new incoming people, the nuclear physics graduates, the new engineering graduates. So what we've done is we've had partnerships with universities where we will fund things like master's programs, PhD programs, and then there will be jobs available for these individuals straight afterwards. And in recent, certainly within the last year, we've made a lot of announcements actually about recruiting directly these engineering students straight from university and putting them straight into work for us. And it's part of obviously ensuring that we've got the workforce to actually realize our ambitions, because we're going to need a lot of nuclear engineers, and they are going to be very heavily fought over, especially with this resurgent interest. And there is that gap that was created by that decline in nuclear. So there aren't enough personnel, I think, to satisfy the demands of all these SMR companies, enrichment companies, deconversion companies as well. So.
What's in the way? Are we over-regulated, or do we need to change how we regulate this low-grade level of nuclear? Are we dealing with the same type of security and regulatory oversight in the high grade materials versus the materials you're dealing with, or is it a lot easier to get into that side of things?
So I think you're hitting upon the right point. I would say not the biggest obstacle exactly, but one of the obstacles that does need to be navigated to put out a commercial product is the regulator. Now, the US is the oldest nuclear energy power in the world, and that basically means that the regulator is one of the oldest in the world too. It has had decades and decades to increase the licensing requirements around the designs, and therefore it does have a very big bureaucratic element to it. This is partly why nuclear energy in the United States is the most expensive nuclear energy in the world. The US is definitely aware of this issue, and the government has actually put mandates on the regulator to reform in the form of like the Advance Act, which includes provisions within it, say, mandating that the regulator takes a maximum of 25-month period to license a new reactor system. And with obviously that, they are aware of the issue and they are putting pressure on there. And the NRC, the Nuclear Regulatory Commission, it does have entrenched systems, but it is making efforts to reform now. And it is looking at different frameworks for new technologies. A lot of these new SMR designs, microreactor designs, they are not novel exactly, but the NRC is not as experienced in licensing these systems as it is with a conventional water-based reactor system. So it is making efforts. It's looking at, should certain frameworks be reformed or should new frameworks be brought in? And they are obviously making these endeavors now, but they are trying to basically catch up with a private industry that is trying to move a lot faster than they might be able to. So it certainly is something that needs to be navigated. And I wouldn't call it an obstacle exactly, but it is an issue that all developers face. So
I see. Yeah, that makes sense. You know, we pay attention to that and try to make it as easy, but also safe, right?
Exactly.
Let's talk a little bit about where this technology can go in the future. Do you think this will work in space? Like if we were going to start to talk about what Musk or others are doing and trying to get more colonization in space, will your technology be able to create power for let's say a station up there?
Yeah, so I'm going to go out on a limb and say that I think the only feasible power for something like a moon base would have to be some sort of nuclear device, because you are going to need a consistent baseload power that can output for a long period of time. And the advantage with uranium is that the energy density is so great that you could not ever ship an equivalent amount of fuel into space to be commensurate with that level of energy because of the energy density. The amount of fuel that you would have to ship to space it would be orders of magnitude, maybe millions of times more cargo that you would have to ship as an alternative to nuclear than a nuclear device. So certainly the first moon bases, Mars bases, wherever you're going you're going to need nuclear power reactors to power these bases.
And does nano nuclear, does it give off as a waste product? Does it give off steam as a natural? Would it still do that same kind of thing? And if so, would it also do that in space?
So the primary output of the reactor system will be the heat that will be generated from the fission of the uranium. And typically, if you think about that standard power station that we were discussing earlier, that heat was in the past used to heat up water to create that steam that would then turn a turbine. It's basically just like a nuclear battery that creates heat that turns turbines. It's effectively on the surface, it's quite basic idea. With these more advanced reactors, you might have a different coolant than water, so some sort of salt-based system with a higher boiling temperature. But the principle is still the same. The heat from the fission product will heat up that coolant, and that heat will be used to turn turbines, to generate that electricity. And if you do that in space, it would be the same principle.
Would you have to capture that release and circle it back through, or would that be released into whatever that atmosphere is up there?
So it's a good question. So it's a closed system. So the coolant that goes through, the heated coolant that goes through to heat to power the turbine, that the process of actually moving that turbine takes the heat off, and so the coolant then returns back to the reactor cooler than it did going into the turbine system. And so you just have that closed loop system where that that coolant essentially does just goes around and around the system.
Right.
All you've got to do is just monitor the chemistry of that coolant. And through that process, that the thing that you're losing to the atmosphere is the heat. But the components and the coolant, they are not lost to the environment at all.
So I get you. So it's closed loop. Heat is the benefit that you're getting from it. So we can capture that for all sorts of different uses, right?
Yes. Like there's going to be industrial heat for any sort of manufacturing that it would need to be done, but then the conversion over to electricity through the turbine system that would power accommodations, desalination, vertical farms, anything like that. So you could have a fairly substantial colony with a very small reactor system. So I would say with one of our ISO container sized reactor systems, you could be powering a community of 1,000, 2,000 people pretty comfortably.
And how far away from deployment are you, let's say, of getting this accomplished?
So it actually comes back to the regulator, I would say. So if it wasn't, a lot of reactor companies have put out timelines like 2027, 2028, and they are completely feasible based on the fact that they can realize this technology in time. We have moved our deployment timelines to about 2030, 2031, but that factors into consideration the licensing with the regulator.
Yes.
The fact that the US does need to rebuild a portion of its infrastructure to support the manufacture of the fuel that would need to go into these. But factoring into consideration those considerations, early 2030s, 2030, 2031 is a very reasonable timeline for when we can mass manufacture these systems and deploy them to market.
Okay, so getting to mass production, scaling and production, of course, we got to have physical prototypes built that would match up with mass production, methodologies. When you build your first prototypes, do you build them just to get them to function, or are you also incorporating your mass scale manufacturing knowledge to make sure your prototype represents what it would look like at scale?
That's a great question, because part of the construction of that prototype will be looking at how we will be able to mass manufacture these systems. So we want to reduce the reactor to the most simple design it can possibly be to aid in the mass manufacture. And the advantage with smaller systems is if you take a conventional civil nuclear power plant, if you shrink it down to small modular reactor level, it gets more simple, less mechanically complex. By the time you get it to microreactor level, it's basically as simple as you could possibly make a nuclear device. And that allows for you to utilize manufacturing processes like 3D printing, where a lot of it could just be put on an automated schedule of the major components being produced and then essentially assembled within a plant and to go out. The prototype will certainly be looking at what can be 3D printed, what can be simplified, and that will form the basis of how we build the manufacturing facilities to produce that. And there will be some concurrent activity as we are building that prototype and getting it licensed. The design that goes into the manufacturing facilities will come out of that work, and so the manufacturing facilities will be produced concurrently with the prototype construction and the licensing of that prototype.
I see. So are you, how many years away are you at getting one of those prototypes built?
We would obviously like to start on it straight away. I think we're going to do in the next year some very significant test work just to make sure the coolant can stand up to irradiation, the materials can stand up to the heat transfer and the thermal conductivity. When we have all of that information, we'll start on the prototype construction. I imagine that's likely going to start next year. We already have the sites in mind where we're going to build this and the teams that we're going to be building this with. We just need to do that initial investigatory work to be confident of what we're going to build. It would even be great if we can get some of that work started at the end of this year, where we begin to look at some of the final design work for the prototype, preparing the site and putting in place the staff. But certainly next year, that prototype construction will begin.
Well, James, that's really exciting. I mean, that's a very, it's a great development. I wish you the best of luck with everything you're working on. And hopefully those regulators can work with you and not against you some more and speed up that timeline. As we all know, the draw on you, who would have thought? Everybody years ago thought, well, we're going to conserve and we're not going to need that much power. But the opposites happen. Now it's just we've got all these devices and everything just needs more and more and more energy. So what an interesting life span of life we've gone through so far.
Yeah.
So I wish you luck, because we really need this form of technology going forward.
Look, George, it's been very interesting talking to you. And look, you're 100% right. Like even if you talk to the tech companies, some of the power requirements that they're projecting that they'll need are crazy numbers. Almost a third as much as the US is using at the moment for themselves.
Wow.
And that's why, like, you see the Googles, the Amazons, the Microsofts of the world going big into nuclear now, because they've got these big power requirements, and I wouldn't say they're panicking, but they need to de-risk their business, and they've settled on nuclear as being that solution. So we're going to need a lot more power. It's looking very likely that for a long time to come, we're going to have to develop these nuclear capabilities and these devices.
Well, thanks for all your work. I mean, James, I wish you the best of luck, and I want to thank you for being on Tomorrow's World Today. That's it for today.
Thank you, George.
Thank you, James.
Thank you for listening to this episode of Tomorrow's World Today podcast. Join us next time as we continue to explore the worlds of inspiration, creation, innovation, and production. Discover more at tomorrowsworldtoday.com, connect with us on social media at TWT Explore, and find us wherever podcasts are available.